welcome to the lecture number 12 of fuzzy sets, logic and systems and applications. This lecture will cover the properties of fuzzy sets. So, in a way here we have the set properties, and we will see whether fuzzy sets also follow these properties or not. And we already know that the classical sets follow these properties, and these properties are law of contradiction, law of excluded middle, idempotency, involution, commutativity, associativity, distributivity, absorption of complement, De Morgan laws. So, these are the properties that we know that classical sets follow, but let us see whether the fuzzy sets also follow these properties or not. So, if we compare the crisp sets and fuzzy sets, we see that three properties are not followed by the fuzzy sets, like we have a law of contradiction. So, when we use fuzzy sets instead of crisp sets, we see that there is a contradiction, and so that is why the law of contradiction comes into picture. And similarly, the law of excluded middle also comes, and another one, the third one, the absorption of complement, that is not followed by the fuzzy sets. And as we move further in this lecture, we will verify these properties for both continuous and discrete fuzzy sets through various examples. So, let us now discuss the set theoretic properties one by one, and first one is the law of contradiction. So, let us take first crisp set and see what is happening with the crisp set if we take intersection of A and its complement. So, if we take any crisp set A, the intersection of its complement always is equal to a null set. Now, if we take the case of fuzzy set, so let us say we have a fuzzy set A, and we do the same intersection, we take the same intersection on this fuzzy set A and its complement. So, this intersection is never a null set. So, we clearly see that crisp set, there is a difference in the intersection of crisp set and its complement, and then intersection between fuzzy set and its complement. And this has been clearly mentioned here that if we have a crisp set A, intersection between its complement is a null set, and if A is a fuzzy set, A intersection A bar is not equal to phi, that means not a null set. So, we will take example here, one example here, and we will see how if a fuzzy set we have, and then how what happens when we take the intersection of a fuzzy set and its complement. So, and of course, this is since this is not followed. So, this contradicts, right. So, there is a contradiction. So, contradiction means if we take a crisp set, we get a null set as a result, and if we take fuzzy set, we get a set which is not a null set as a result. So, that is why there is a contradiction, and that is how this is called the law of contradiction. So, if we take an example here, we take a fuzzy set A, which is a triangular fuzzy set, and this fuzzy set is defined by a triangular membership function. So, this is a triangular membership function here, but the whole thing is called the A fuzzy set A fuzzy set A. So, as we are trying to verify whether A intersection A bar is null or not. So, let us now first have A here and then try to find A bar. So, A bar is the complement of A. So, we see here there is a complement of a fuzzy set, which is represented by the green color. So, this is we can say the complement of fuzzy set A, and this will be denoted by A bar, which is complement of fuzzy set A, and this is a fuzzy set A, fuzzy set A. So, if we take intersection of these two fuzzy sets, so we already know if we are taking the intersection of any two fuzzy sets, we follow the criteria, we follow the condition as the min, we take the minimum of the membership values of the corresponding generic variable values at each and every point. And this is needless to say that all of these generic variable values must belong to the universe of discourse. So, here we have the A intersection A bar. So, these two A fuzzy set and A bar have been overlapped or superimposed to find the intersection of these two fuzzy sets. So, it is very clear here, if we apply this criteria, this condition, we see that we are getting this red, the portion which is marked by red color. So, this portion is basically the A intersection A bar, which is represented here by this separately by this membership function. So, this is nothing but A intersection A bar, and we clearly see that this is not a null set, means we are getting something here, we are getting a fuzzy set here. So, obviously, this is not equal to phi, means this is not equal to, this is not a null set. So, we can clearly say that the law of contradiction is verified. Now, if we take, so this was the example when we took triangular fuzzy set. So, obviously, it was a continuous fuzzy set, but if we take the discrete fuzzy set just to see whether this law of contradiction is verified for discrete fuzzy sets also. So, Let us take an example here, and this example is with discrete fuzzy set. So, this is a discrete fuzzy set A, discrete fuzzy set, and if we try to find the A bar of it, the complement of the fuzzy set A is complement of fuzzy set A, and this is nothing but A bar as it is written here. So, if we take the intersection of these two fuzzy sets, again we see that we get something here which is not equal to the null set. So, it means that here also we are getting a set which is not a null set. So, we can say that the law of contradiction here also is verified. Then we have another set theoretic property, and this is called the law of excluded middle. So, if we take why is it called law of excluded middle, we will get to know in a moment. So, if we have crisp set A, and if we take the union of A and its complement. So, for crisp sets we always get the universe of discourse as a result, whereas if we take a fuzzy set A and if we do the same operation, means we take the union of fuzzy set A and its complement, this is never going to be the universe of discourse. So, here we have clear cut difference in between the crisp set, the union of crisp set and fuzzy sets. So, we call this discrepancy as this contradiction as the law of excluded middle. So, here as I already mentioned that if we take crisp set A, if we take union of A and its complement, we should get the whole universe of discourse, whereas if we take fuzzy set A, the union of fuzzy set A and the complement of fuzzy set A is not going to give you the universe of discourse. So, that is what is the difference, and this is called the law of excluded middle. So, let us understand this law of excluded middle better by taking an example, and here also we have taken a continuous fuzzy set which is triangular. So, if we take a fuzzy set A here and the complement of this fuzzy set A is here, and if we take the union of these two fuzzy sets. So, here we have superimposed this fuzzy set which is A bar complement of this fuzzy set, right. So, if we apply the condition of the union, the criteria which is here, we take the max of all the corresponding membership values of the two fuzzy sets A and A bar with respect to the generic variable values in the universe of discourse. So, what we get here is this, which is represented by the red color. So, we get, if we take the max, we get this portion, right, and here we apply the max of the corresponding membership values of the two fuzzy sets corresponding to the generic variable values within the universe of discourse. So, if we separately represent this, it looks like this. So, here is what we are going to get as a result of a fuzzy set A union A bar, and which of course is not the universe of discourse. So, what do we mean by this statement when we are saying that this is not equal to the universe of discourse? So, when this would have been the universe of discourse, so when we would have got this as the straight line like this. So, this portion should not have been there, then we would have said that the A union A bar is equal to the universe of discourse. But since here this is not exactly what I mean the straight line, we have this portion also. So, we call this as this here as the A union A bar is something which is not equal to the universe of discourse. So, this clearly gives us the idea as to how we check when we take the union of any fuzzy set and its complement. So, this is how the law of excluded middle is verified for a fuzzy set. Similarly, we can take the example of discrete fuzzy set here you see, and then if we find the A bar which is the complement of a fuzzy set A which was taken here, which is taken here, and we see that this is the complement of the fuzzy set A taken in this example, which is also discrete, and if we take A union A bar, we get something here and which is not equal to the universe of discourse. So, here also this is true, that the law of excluded middle is verified for any discrete fuzzy set. Now, we have another set theoretic property which is idempotency. So, let us now take a crisp set first and see how this idempotency property is verified for a crisp set. So, A intersection A means if we take the intersection of the same set, we always get as a result the same set, means if we take the intersection of A and A, we get the same set. So, which is here the same set is a crisp set which was taken. Then again if we take the union of a set with this same set, we are going to get the same set. So, this is known for crisp set, which is which we have already done so many times in the past, but if we take fuzzy set, let us see what happens. So, if we take fuzzy set here A, so this is fuzzy set A and this is also fuzzy set A, fuzzy set, and this is also fuzzy set. So, if we take the intersection of the same fuzzy sets, we are going to get the fuzzy set, same fuzzy set, means A intersection A, or we say fuzzy set A intersection fuzzy set A, we are going to get fuzzy set A. Similarly, we take union, it is going to return the same set, and this is called the idempotency property. So, what we see here is that we get the same set whether we take a crisp set or a fuzzy set. So, that is how the idempotency property is verified for both the kinds of sets. Let us take an example to better understand this property. So, if we take a triangular fuzzy set, if we take a fuzzy set here as A. So, since we would like to verify the idempotency property, so we have to have the A union A and A intersection of A, and we see what we are getting as a result of it. So, here we have A, and then here we have A intersection A. So, if we intersect these two fuzzy sets, we are going to get the same set. Similarly, if we are doing here, if we are taking the union of it, we are going to get the same set. So, this way we can say the idempotency property is verified for fuzzy sets. So, if we take this as the fuzzy set here, which is discrete, and if we try to find the A union A. So, we see that A union here also is A union A here also is coming out to be A. Similarly, if we do this operation, we take A intersection A, we are going to get A. So, this way we can say the idempotency property is satisfied or verified for fuzzy sets also, because the crisp set this property is satisfied. So, here also for fuzzy sets this property holds good. Then comes the involution property. So, this means that if you take any crisp set A and then you take the complement of this crisp set twice, means you take A double bar. So, what does this mean is that if we take a crisp set A, we take the complement of it and then we further take the complement of it, and this is going to return us the crisp set which was originally taken. So, this is the crisp set, this is this crisp set which was originally taken. So, this is going to return us the same set. So, let us see this involution property holds good for fuzzy sets also. So, if we take a fuzzy set A and if we take the double complement, so it means that if we take the complement of a fuzzy set and then we take further complement of it, here also this is going to return us the same fuzzy set, which was used for taking the complement. So, it means if we take the double complement of any set, it is going to return us the same set, and this is true for both the cases, means the if we take crisp set or the fuzzy set, both the cases we are going to get the same set. So, but we are here interested more on fuzzy sets. So, we can clearly say that if we take a fuzzy set A and then if we take the double complement of it, we are going to get the same fuzzy set as a result. Let us now understand better this involution property for fuzzy set. So, let us take an example here, and if we take a fuzzy set A and let us now take the complement of it. So, here we have the fuzzy set, the original fuzzy set which we have taken, and then the complement is here. Now, if we take the double complement, see the double complement here, and which is nothing but the same set. If we see here, we are going to get the A. This set and this set is coming out to be the same. So, double complement of any fuzzy set is going to return us the same fuzzy set. So, this way we can say that the involution property is verified for continuous fuzzy sets. So, let us now understand this for discrete fuzzy sets also. So, if we take here an example of discrete fuzzy set which is here. So, let us take the complement of it. So, this gives us the complement of A, that is A bar. So, this is represented by this discrete fuzzy set, and if we take the double complement of is double complement means further complement of. So, complement of A bar, and this is going to give us A double bar, and this is the A bar, and which if we see is the same set which we have taken, we have started with. So, if we see that these two sets remain the same. So, we can clearly say that we are going to get the same set if we are taking the double complement of it, and this property is nothing but the involution property. So, this is verified. So, in this lecture today, we have studied the following properties of fuzzy sets, and these properties are law of contradiction, law of excluded middle, idempotency property, involution property. So, but here we have so many other properties left which we will be discussing in the next lecture.